Hi everyone, this is question 3 of NZQA Scholarship Physics 2022. This question is called Magnet Slider. A metal roller of mass m slides without friction down parallel conducting rails of negligible electrical resistance. The rails are separated by a distance L and are connected to each other at the bottom by a resistance R, forming a closed rectangular conducting loop with the rails and the roller. The plane of the rails makes an angle theta with the horizontal, and a uniform vertical magnetic field B exists throughout the region. As the metal roller slides down the rails through the magnetic field, it reaches a constant velocity v. Show that the constant velocity achieved by the roller through the magnetic field is given by the relationship v equals and then so on. So looking at this, it's very easy to be intimidated because it's a bunch of random symbols and you have no idea how they even got to this point. They tell us it's constant velocity, so we will use that fact. And what I like to do is I sort of like to work backwards. And I like to start with the result. So I like to start with the final equation that they give us and maybe, acquire some hints from this equation. Immediately I see mg. Mg I associate with weight force. And so there is definitely some sort of weight force present in here. And I see B and L. And usually I only see B and L in the equation F equals BIL. So immediately I have two forces. So that force due to a magnetic field and a current, and also the weight force. So they also tell us constant velocity. Immediately I'm thinking, the two forces produced by the wave force of the roller as it is rolling down the two conducting sort of what are they called? Rails. And that counteracts the magnetic force produced by the magnetic field. So we can immediately just start with some forces. So we know that the weight force is equal to the force due to the magnetic field because it's traveling at constant velocity, so the forces are balanced. The weight force here, so let's first start with Fg. The weight force is mg, but because it is acting, the weight force is acting at a component, so we can draw this out sort of like a triangle, theta, and let's say the roll is here. Let me draw that bigger, hold on. So the theta, and then the roller's here, and it has a weight force here, Fw. We are considering this component because that's the component which is actually causing the roller to slide down, and so that is Fg equals Fw, or mg, so mg, and then the component is just given by sine theta, so mg sine theta. So then we can say that this is Fg equals mg, or mg sine theta. Let me just erase that. Okay, great. Now we're trying to figure out Fb, or the magnetic force. So we know Fb equals to BIL, but because magnetic force is actually we are only considering the component of the magnetic force which is acting against the weight force. Well, then we only want to consider a specific component of it, so cosine theta. You can do the trick by yourself and you can figure out why it's sine theta and why it's cosine theta. But let's see. That means if we look at the final equation, I don't see I in there. So I'm trying to get rid of I somehow. And we can do that by seeing, there's an R in here. So at some point we added a resistance, and that's probably right here when we convert I to V over R. So this is Ohm's law. And now we have this voltage here that we also don't have the final equation. So then we can say B, and then I believe this is a formula. V equals, sorry, let me check. Where am I? V equals BVL. So B equals, and then this is BVL. But because the velocity of the roller is not perfectly perpendicular to the magnetic field, again we have to add a component here of cosine theta, R, L, and then cosine theta again. So immediately we see, there's a B squared, there's an L squared, there's a cosine squared theta, there's a V, and then there's an R. Okay, this is starting to look somewhat like the expression we have here. So these two forces are equal to each other. because it's traveling constant velocity. So mg sine theta equals b squared L squared cosine squared theta v, all divided by r. So then v equals, and then we can go mgr sine theta, mgr sine theta. So I'm just rearranging the equation right now. Divided by b squared L squared cosine squared theta. And this looks very similar to the equation up there, except some of our trig functions are a bit off. And this is just a matter of knowing your trig theorems. So hopefully you've studied your trigonometry. So sine theta, and then we know that cosine squared theta. Oh, actually, what might be better to do is to just look at their equation and say mgr, and then just convert that into tan theta. So we know, tan theta, and this is something you have to sort of memorize, equals sine theta divided by cos theta. So we know that sine theta equals tan theta cos theta. So then this is equal to tan theta cos theta, and then b squared L squared cos squared theta. And we can see that that cos theta and that cos, or that square of the cos theta will cancel. And so we get mgr tangent theta divided by b squared L squared cos theta. And that is exactly what we have here. So now we move on to part 2 of question 3a. Explain what difference, if any, it makes to the constant velocity v if the magnetic field is in the opposite direction. Intuitively, you can sort of see that if the roller were to move down this setup, that the constant velocity wouldn't magically change if the magnetic field was in the opposite direction. It wouldn't. The velocity of the roller wouldn't suddenly go back up. You don't expect it to move against gravity somehow. But we can prove this. So our conjecture could be there's no difference, which is correct. No difference. But let's prove it. So what's actually causing the magnetic force here? F equals BIL, just as a simplification. In this case, B would be reversed. So B is reversed. And so maybe you'd expect force to be reversed. But there's something else we have to consider here, and that's the current. What's happened here is that the current produced by the slider rolling through, if you sort of use your right hand and do your right hand rules, you'll find that the current is also reversed. So current is reversed. And so what happens is the effects of reversing both the magnetic field and the current would cause the force to remain the same. And so again, no difference on the constant velocity v. So now I move on to part B of question 3. For small values of theta, equation number 1 may be approximated as that formula, equation number 2. And they tell us an experiment is set up with B equals 2 teslas, L equals 0.5 meters, M equals 5 times 10 to the negative 3 kilos, and R is equal to 10 ohms. Determine the accuracy of equation number 2 with equation number 1 at theta equals 25 degrees or 0.436 radians. So to determine the accuracy, you could just do percentage difference, because that would tell you sort of how accurate equation number 2 is compared with equation number 1. And we know equation number 1 is theoretically correct because we have proved it with physical principles without any major assumptions. So percentage difference is equal to, it's equal to the actual value minus the approximate value divided by the actual value. Usually you sort of see literature minus, so theoretical minus experimental divided by theoretical. So it's sort of the same idea here. Okay, now we just have to figure out what these values are. So actual, the V is equal to, and this is just a matter of plugging into this formula up here many times. So mgr tan theta b squared L squared cos theta. So now we just substitute. And okay, well, you can substitute by yourself, but if you make all the substitutions correctly, you would get 0.252 meters per second. And then the approximate of V equals mgr b squared L squared, and then theta plus 5 theta cubed divided by 6. Okay, and then once you make all the substitutions again, and for this one, you have to use theta as radians, because Well, they don't tell us that it should be in radians, but if you do use degrees, you would end up with a very large number because you would have 25 cubed over here, and that would sort of tip you off that something was wrong, and then you start using radians again. But this would give you a value of 0.248 meters per second as long as you use radians. Okay, so then the percentage difference is equal to 0.252 minus 0.248, so the actual minus the approximate, and divided by the actual, which is 0.252 again. And that gives us 1.6%. So now you know the percentage difference between the equation number 2, which is our approximation, and equation number 1, which is our theoretically correct equation, is 1.6%. And basically you can use that percentage to gauge the accuracy of equation number 2 compared with equation number 1. So now we move on to part C of question 3. By calculating the velocity at the high angle of theta equals 85 degrees, explain if this equipment would be suitable for testing whether equation number 1 is accurate at high angles of theta. Okay, so again, we make another substitution. So V equals, and then we go mgr tangent theta divided by b squared r squared cos theta. And this time we just plug in 85 degrees instead of 25 degrees. So 5 times 10 to the negative 3 times 9.81 times 10 ohms times tangent 85 degrees divided by b squared, so 2 squared times, and then l squared is 0.5 squared times cos 85. We get we get a velocity of 64.3 meters per second. This velocity is incredibly large. It's what you'd expect here then is, even if the ramp were 60 meters long, then it would only go through the magnetic field for 1 second. And right now our ramp is only half a meter long. So compared to the ramp that we actually have, the magnetic roller, or the magnetic roller would not be able to roll through the magnetic field in a long enough time for us to make good measurements. So basically we can say velocity is too high and then unable to make good measurements, and then it's not suitable for testing whether equation number 1 is accurate. Okay, great. Now we do part D of question 3. Explain whether equation number 1 remains valid if the roller rolls rather than slides down the slope. Okay, equation 1. If we remember back to our derivation of equation 1, we started with Fg equals Fb. So the rate force is equal to magnetic force. And what I like to do is, basically, if anywhere along our derivation we have sort of a discrepancy between whether or not, or whether the roller rolling has an effect on the derivation. If it does have an effect, then equation number 1 is no longer valid. But if at no point during the derivation would the rolling have an effect on the derivation, well, then equation number 1 should remain valid. So let's move back to our derivation here. So we started with comparing the weight force with the gravitational force. This is fine. Doesn't matter whether or not it's rolling or not. It's still, the weight force is still equal to the magnetic force. This is also fine, because it doesn't matter whether it's rolling or not. The weight force is still equal to mg times the component. And this is also fine, because the magnetic force is still equal to magnetic field strength times current times length. Doesn't matter whether or not the roller is rolling or not. And you can see everywhere along the derivation. So here we're just substituting for Ohm's law. Obviously the rolling does not affect that. Here we're just substituting again, and here simplifying. Here we are rearranging. Here we're equating. Here we're rearranging. And basically nowhere along this derivation does the fact that the roller rolling have an effect on the derivation. And so we can say that rolling has no effect on derivation. And so therefore equation number 1 remains valid.